Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to discuss a topic in electric charge, and this is going to entail specifically the work and energy in relationship to the force of a charge that is moving maybe in a potential difference. And we're going to see that this relationship, of course, can be either be applied in different ways in order to find solutions to problems like the one that I've listed on the board. So without further ado, thank you and welcome. So our topic for discussion for today is going to be the concept of energy and work. And of course, this is in relation to an electric charge that we have already discussed in one of our videos on when we were talking about the concept of an electric field. So in this case, we're going to use the sample question on the board in order to find out what relationship exists between this concept of energy work and maybe the forces which are expressed by an electric or a charged particle. So for that case, we're going to start with defining the concept of electric potential. And from the concept of energy, we know that energy can be maybe explained in different or maybe expressed in different forms. So therefore, we have different forms of energy. And from the law of conservation of energy, we know that energy can be able to be, or can change from one form to another. And therefore, this is one of the areas which is going to be applicable in this particular discussion, whereby we are having an electron that is moving, and of course in from a stationary point with a charge, and then maybe going to its final destination and covering some distance. So there's a relationship between these particular aspects that I've talked about, whereby we have an electron, of course, which is carrying a particular charge. We're going to see that this specific charge for an electron is a constant. Of course, we're going to look at it later, but I can just mention it here for the sake of remembrance. So also it's covering from a stationary point. Maybe we can give that point as a point P, and then to a final point Q, and whereby of course there's a distance that is covered between R and Q, or perhaps I can be able to give it as an initial point R1 and the final point R2, and there's a charge that of course is of this initial point, which we are going to represent by Q, of course, being given as 2.010 negative 9 coulombs. These are just information that I'm trying to extract from this. And there's a distance, a difference between these 2 points, whereby we have been given one is 120 and another one is 18. But that's a point for our discussion later. So this information that we get from the question is going to lay a basis for us in trying to understand the concept of electric potential. And so therefore, we just go ahead and try to figure out what this concept of electrical or electric potential stands for. Now, when we were trying to talk about the concept of an electric field, we said that these are lines or maybe force that move that is experienced between 2 points which are charged. Let's try to just illustrate that those two specific points, or maybe areas, of course, are positive or negative charge. Now, from Coulomb's laws of attraction, we know that there will be an attraction between these two charges. And therefore, maybe if we have a particle that is at rest at this specific point, and then it's meant to move. So this is an electron. So basically, due to the forces of attraction or the laws of attraction, it's going to move in that direction. Or maybe it's accelerated, then it's going to move in that direction. And in this case, because of a difference in direction, it's going to perform some work in order to overcome the resistance or so basically it's going to perform some work in that particular field in order to assist it move from the point maybe R1 to R2. So therefore, if that is the case, then we're going to see that a charge moving in an electric field, which we can denote. Now this electric field, of course, we can be able to do this whole region that is having charge, we can denote it using the letter E for an electric field. So an electron moving in this particular electric field is going to experience a force, which is given as force is equals charge times E, whereby already we have defined E, but we are going to see its implications as we move ahead. So in this case, there'll be work done on the charge by the field as it work done on the charge by the field as it moves from point R1 to R2, and this as well where can be given a relationship which can be illustrated as work is the summation of all the small elements of work done from point R1 to R2. And basically from our classical definition, we know that work can be represented as a product of force times distance. So I'm just going to give it as W equals the integral of 1 from 1 to R2 F dot ds. So basically, as I've said, this gives all the sum of the elements of work along the path. And this can be given still as this element of work can be given as dW F ds to represent the work done along that path. So this form of an equation is going to assist us to find out how we can be able to represent work when F that we have mentioned here, which is involved, in that case, which is a force. This implies an electrostatic force in that particular field. And therefore, we're going to find the relationship between that force and the work that is done, whereby from this definition of force, we can be able to do a substitution in the second case. Let's say this is our equation 1. Therefore, I'm going to do away with this. We can be able to represent the W in form of a QE by writing W from R1 to R2 QE, which represents force, electrostatic force, ds given as such. Now from the laws of integral, we know that because Q is a constant, we're going just to make it out, and then we shall have this one represented as Q E S. So that is basically going to give us the work that is done along that particular electric field. And we know that electric force is a conservative force, and this in a sense can give us a way in which we can be able to calculate the potential energy in this particular field. We know that potential energy is given as this is the initial U, basically implying potential energy. So we have seen that due to the fact that electrical force is a conservative force, this can give us a sense of trying to figure out how to find the electric potential energy, of course, between the 2 points. Now in this case, we're going to see that therefore the change in potential energy is the one that is going to bear significance in our particular case. And we're going to define this change in from the work energy theorem. We know that change in potential energy basically implies work, and we're going to see how the work energy theorem, the work energy theorem can be able to be related to kinetic energy and loss in potential energy in that case. So by definition, therefore, we are going to see that the change in potential is a negative of the work done by an electric field. So this particular change in potential delta U is going to be the negative work done by the electric field. And we have said that the work done can be represented using those two specific equations. So therefore, the implication of this negative sign is going to give give us the negative, the integral from R1, R2, E ds. And in this case, of course, we can be able to find potential energy at a specific point by making what we call a point of reference. So in this case, we need a point of reference in order to define the potential energy that is going to be involved in moving this specific particle in an environment of what we call the electric field. So this basically entails the concept that the potential at the energy at infinity will be able to R is basically equals to 0. Now that one will make it as a point of reference, and therefore that one will assist us to find the difference in potential energy between R1 and R2. Now there's a relationship that I want us to be of course keen on, whereby, as we have said, from this particular definition, we're going to find the difference in potential energy between R1 and R2. So therefore, we're going to make R1 our point of reference in trying to find that specific energy. So in this case, the change in potential, we have said it will be change in kinetic. I mean change in the potential energy divided by the charge. And therefore, this is going to have an implication on our equation, which we have listed. Our last equation that we have already mentioned on this, the element of charge is going to cancel out. So therefore, we're going to have the change in the potential given as the negative R1, R2, E ds. So at that specific point, that is going to give us the change in potential energy, and we're going to see that the product of this basically, or the result of this, is going to be a quantity whose unit is going to be, of course, we're going to mention it, because this is going to give us another way in which we can be able to illustrate that form of energy that is resulting from that. So I'm just going to do away with that. So therefore, that change in energy is going to be a scalar quantity. We've talked about the concept of scalar and vector quantities. And of course, this is going to be a scalar quantity with the units of joules per coulomb, which basically implies the concept of volts. So therefore, joule per coulomb is for a unit is going to be joule. And given the relationship between this one that we have talked, so 1 volt will be represented as 1V, which is 1 joule per coulomb. And now from this relationship that we have given, this implies that the product of the potential energy and the charge is going to give us energy in joules. So V 1V dot 1C J is equals V dot C. So basically, multiplying our charge times a potential difference gives the energy, which is going to give us the product of, for our case here, this is an electron, therefore it's going to have a charge which is E, and this one is going to give for potential energy volt. So therefore, this is going to give us the concept of electron volt, which is denoted as EV. So if you try to look at this, we have tried to make a merge of those specific concepts, and there's a constant that are written here, and they said that we just reserve it for the further discussion. So this is the point at which I'm going to define that specific constant for the charge of an electron. So I've talked about the concept of electron volt, and I've shown how we can be able to find it from the dimension that we have given for joules over the charge. So therefore, 1 electron volt is given as 1, or just EV, which of course is a constant times 1v. So as we said, the product of that one is going to give us joules. Therefore, we can illustrate this charge using 1.60 times 10 negative 9 joules. So as we said that the potential energy at infinity can be given as 0, we can choose our point of reference and find a potential function at for all points along the that electric field where the electron is moving, whereby the potential at any specific point can be represented using the integral from our point of reference to point R, E, ds. So therefore, given that we have defined the change in potential energy, the change in our potential between the 2 points of R1 and R2, given as E ds. This is for the general representation of a potential at a particular point in regard to the point of reference. So specifically for us, it's from R1 to R2. So therefore, for the potential due to a point Q that we are being requested to find, the potential due to a point Q or a point of a charge Q can be given as VR KQ over R. Of course, this of course, K is one of the constants that we have been using maybe in some of our videos, and that one represents permittivity or electric permittivity, which is also another. No, that one represents a constant, of course, which entails the concept of electric permittivity, which can be expanded as 4 pi epsilon naught given as such. So this one is just a numerical value, and that is pi, and that is epsilon naught, which I've said is this electric permittivity. Which is a constant, of course, which is given, and therefore the whole concept of this one, the reciprocal of this, entails the concept of K. So therefore, we can give our potential as K QV. We can expand that one to give or maybe to represent that specific formula using that form of K by having V generally represented as Q over 4 pi epsilon naught and then R. So if a point of reference for that case, the initial point for our case, which is initial potential. Initial potential for us is this is U1. Therefore, it's going to be represented as a charge of that electron 4 pi epsilon naught R. So that is the initial point, and then the final point for that specific electron or a point charge, the final point, or the final, this is going to be the final point potential. The final potential for our case U2 is going to be 4 pi epsilon naught R2. This is R1, from R1 to R2. Therefore, we can be able to represent the change in potential by giving change, or maybe RU. This is U minus U2, which is given as QE over 4 pi epsilon naught 1 over R2 minus 1 over R1. So remember that these two specific concepts that we have talked about is a negative. We said that work is a negative. We defined the work done in an electric charge as the change in the potential, which is a negative of work done by an electric field. So these two specific potentials for this one is negative Q, and this one is that one. So therefore, generally we are going to have our representation for change in potential being given as such, and that is the concept that we are going to use in order to find the speed of that electron. Now in this case, from this particular case, the change in potential energy, I said, is the kinetic energy. Loss in potential energy is equivalent to kinetic energy, and that is from the work energy theorem, which of course I mentioned somewhere in between our discussion. So I'm just going to give that relationship so that we can be able to have a conclusion on that. So basically, by the work energy theorem, so the gain in kinetic energy is equals loss in potential energy, and therefore we can be able to represent this one as kinetic energy gained, which is the change in potential energy, which we have represented as this 1 over R2 minus 1 over R1. So the negative signs that were here have had an implication on the position of these two specific for R1 and R2 respectively. So you can confirm that one. So basically in this case we are looking for the speed, and from kinetic energy this is what is going to give us the speed of this particular particle. So therefore we're going to make V the subject of the formula, and we can just going to write it for the sake of space. This is going to be V equals 2QE all over 4 pi epsilon naught m. M in this case represents the mass of that specific particle. Now for an electron, that mass is a constant. So therefore we are going to have this one represented as 1 over R2 minus 1 over R1. The root of that. So remember this V was just a square. So therefore that is going to be the root of that. Now if we do a substitution in this, we're going to have 2 times Q is 2 times 10 negative 9 coulombs times E. The value for E we said is an electron charge, which is 1.6 10 negative 19 coulombs. So that one divided by 4. So all of this specifically, which entails constants, this is a mass of an electron, permittivity by 4. It's going to give us the product of 9.1 times 10 negative that 1. And then there is another factor, of course, which I'm just going to list on this other side, which basically is going to be times 9 . Now we're going to see that the loss of indices, when we have a negative sign and a positive one, it's going to have an implication. I've just done a rearrangement of that specific formula in order to get adjust for space. So I'm going to do this one, and we can do a substitution to confirm whether the calculation is correct. So this is 1 over R2, 0. This was 18 centimeters minus 1 over 1.2. I've converted those specific measurements in length into meters, so this is going to be the root of that. So specifically this is going to give us the speed of an electron, which is going to be 5.467 times 10 6 meters per second. So basically, because of the size of our space, I'll request us to just go and do a confirmation for the multiplication. But in an essence, at this point, this is the formula for finding the speed of this specific particle that we are talking about. So therefore, we can use the work energy theorem to ascertain for this relationship between this. So basically, it entails all of this in order to find the relationship that we have been asked. So in our discussion, basically, we have touched on the concept of energy and the work from the work energy theorem that I mentioned about, and an electric charge that we had given, of course, from this formula of the product of charge and the potential in an electric field E given as such. So I hope that this is going to assist us in maybe a question we have just used here to try and discuss the concepts which have been mentioned here. And this basically are going to assist us in trying to find the relationship between maybe this charge, work, energy, and the kinetic energy that we've talked about, in trying to find the relationship between electric work and energy. So I hope that the discussion has assisted us into trying to find out how we can be able to work on work energy insofar as electric charge is concerned. This one, together with other discussions, are going to assist us in trying to figure out on how to work some of the problems that we may encounter in electrostatics and other fields which are related to this. So for that case, that is it for today. Bye guys. God bless.